Hello, my name is Patricia Rose De Leon, and today I will be doing the third reading aloud assignment, which is on chapter 3 that focuses on the resting cell membrane potential. And yeah, let's just get started. And before I actually do the think aloud assignment, just to let you guys know that I will start from the left and then move on to the right, just so you can see the order in which I'm reading the text in. Okay. So figure 3.5. Common ion channels in the axon membrane. A. Most potassium channels are open and most potassium ions are inside the axons are inside the axon. Because as we can see here, um yeah, I can definitely see how like the channels are open. Um there's no one of these square. I'm not sure what's the right term for it, but I'm just gonna depict them based on what they're being visually represented. So yeah, we can see here that the channels are open because none of these square things are blocking the axon pathways, and I think these dots are um, the the potassium ions. This is the bottom part is the inside of the axon, the top part is the outside of the axon. So yeah, these so basically this shows how potassium channels are open and the ions most of the ions are inside the axon. Okay, so B. Most sodium channels are closed and most sodium ions are outside the axons. So compared to the first one, um, so compared to the first example, most of the ions are inside the axon. But in um, this second example is most of the ions are outside of the axon. As we can see here, I feel it seems like only one channel is open. There's a few ions inside the axon, but most of them are outside. And C. Chloride channels are open, and most chloride ions are outside, but there are not as many chloride channels as potassium and sodium channels. Okay, so in the potassium channels, there's more in the inside of the axons. There's more ions in the inside of the axons. In the sodium channels, there's more ions in the outside of the axon. But in the chloride channels, most of the ions are in the outside, but there's not as many chloride channels compared to the other channels. So we can see here that there's like only a few of these rectangles. I guess they represent the channels. And yeah, I guess the main difference is that I think the potassium channels and the sodium channels have like an equal amount of channels. But I guess for the chloride channels, there's only like a few of them. So yeah, I would say it's pretty similar. The amount of ions outside of the axon are pretty similar to the sodium channels. There's fewer on the inside axons than there is on the outside axons, which is pretty similar to the sodium channels. Okay, so there are two types of ion channel: a voltage gated and a chemical gated. The gates on gated ion channels are complex protein molecules that respond to changes in the membrane potential, that is, the voltage difference across the cell membrane. And if the voltage changes, more gates may open or close. The other type of channel is the chemical gated ion channel, to be discussed in chapter 4. Okay. So basically, I think voltage gated channels, they like open in response to changes in like the electrical charge and across the membrane. What this basically means is that um it opens channels which allows like the movement of ions along those like electrochemical processes along the cell membranes. Okay, so in In chemically gated channels, the gates are chemical receptors. Complex. Okay, I should probably remember this. So, chemical receptors are complex protein molecules that respond to a chemical transmitter. Typically, a neurotransmitter, I know what that is, I learned that in my AP psychology class, released at a synapse, rather than to changes in membrane potential. So, when a chemical neurotransmitter acts on its chemical gate, to depolarize the membrane, voltage-gated channels may also be activated. The protein gates of voltage and chemical channels are okay. It kind of got cut off there, but okay. Okay, so I think the main difference between these two ion channels is that because um, the voltage gated channels, they're used to open and close in response to changes in the voltage or the membrane potential, which is like I think involved in generating action potentials. And I think the chemically gated channels, they're used for like open and close in response to chemicals such as neurotransmitters. Okay, moving on page 59, membranes and potential, and it will be about resting cell membrane potential. Okay, so most living cells maintain a potential difference. It is a voltage difference across the cell membrane. Let us first consider an idealized cell that has no fibers. If we were used to if we were u- if we were to use a microelectrode to penetrate the cell membrane and record the voltage difference between the inside and the outside of the cell, we will find that the inside of the cell was about negative 75 millivolts relative to the outside. This is nearly one tenth of a volt. 1 volt is a thousand millivolts. Okay, 1 volt is a thousand millivolts. Probably might be useful for like conversions and dimension analysis. Okay, so very substantial voltage for a tiny cell to maintain. So basically, potential difference is like this kind of difference between um this difference of like electrical potential between like 2 points, or I think it's um it basically represents like the kind of work involved or the energy that is released in like the transfer of a unit or a unit quantity of like electricity from like one point to another. So that's I think basically the potential difference. Okay, so figure 3.6. The resting cell membrane is in an idealized cell is negative 75 millivolts inside relative to outside. The potential exists only across the cell membrane as shown in figure A. Okay. Okay. Yeah, I could definitely see here um how the negative 75 millivolts is um in the inside compared to the outside. I'm not sure how to interpret it. I'm not sure how to interpret this graph right here, but I might look that up later. Okay, so the outside medium is electrically neutral. B and B. Yeah, oh, okay. It's neutral because it's set on zero, as the cytoplasm inside C. What's the difference between B and C? They look pretty much the same. Oh, okay. Oh, okay. I was talking about the cytoplasm. Okay, yeah. Because um, here it's talking about the outside medium, but in here it's talking about the inside of the cytoplasm. But they're both the same um charge. Okay, so indeed the electrode is shown penetrating the membrane at, ti- at time t1, and the measured potential immediately drops from 0 to negative 75 millivolts. Okay. So from here, it remain neutral, but then it drops from T1. Okay. So microelectrode penetrates through the cell membrane at T1. So which is where it drops from 0 to negative 75 millivolts. Okay, got it. Might have to look this up on a more um just might look for more clarification later, but overall I kind of get the idea of what this figure is talking about. So a typical non-neural cell might have a resting membrane potential of about negative 75 millivolts, and it does not develop an action potential. The cell has several types of ion channels. All of the open type, the commonest of all of the open type, the commonest of which is the potassium channel. There are enough potassium channels so that the K plus can pass freely back and forth across the membrane. Oh, okay. So, um, potassium channels are basically the most common type of ion channels, and basically they play like a kind of major role in setting the resting membrane potential. So when they are open, the K channels, they kind of like tend to draw the membrane potential that is closer like to the K plus equilibrium potential. So I think that's what it's trying to say here. Okay. So cells contain a considerable amount of protein, whereas there is a very little protein in the tissue fluid outside the cells. Much of the protein inside the cells is in solution as protein ions or charged molecules. The protein ions have a net negative charge p raised to negative 2 raised to 2 negative, since they are too large to pass through the ion channels in the membrane, they remain outside. They remain inside the cell, which is the basic reason why the cell membrane potential is negative inside relative to outside. Oh, okay. Um, I think the membrane is more permeable to K plus than to sodium. I mean, is more permeable to potassium than to sodium because potassium moves down its gradient, basically like out of the cell, which is more like ready than sodium when it moves into the cell. I think this is a pretty important paragraph to discuss because yeah, I think this is pretty important type knowledge to learn because I think the increased flow of like positively charged potassium ions like out of the cell kind of results in this like net negative charge in a way, like a net negative charge inside the cell. So the negative sign, I believe the negative sign in the resting membrane potential kind of represents like the negative environment inside the cell that is like relative to the outside. um, so I think this is why um, potassium has like this increased permeability, but it also has like these increased amount of like electrical force. Okay, moving on. Suppose a typical cell is immersed in a solution containing potassium and chlorine. Remember that potassium ions can cross the cell membrane freely. It is permeable to K plus, just like what I mentioned. Assume that chlorine ions cannot diffuse as much through the cell membrane. There is a very strong force called the diffusion force that acts on ions in solutions to drive them toward equal concentrations throughout the solution. For example, if you drop a pinch of table salt into a glass of water, it will dissolve. In the Na oh wait, in the and the sodium and the chlorine would rapidly be distributed throughout the solution until they are in equal concentrations everywhere. Okay, so I did learn about diffusion force in my AP chemistry class, and so basically diffusion is this kind of like mass transfer that causes like the distribution of like chemical species to become like more uniform in space as like time passes by. At least that's what I remember from my AP class. So basically, diffusion is maybe like the driving forces of diffusion could be through like thermal motion of molecules, and however at temperatures about above like absolute zero, usually these molecules are never at rest. So yeah, I think they kind of provided a great example about how diffusion works. As you can see here, they shown an example of glass water in which sodium, probably like um yeah, oh yeah, it says here a pinch of table salt. Um so the Na, which is the sodium, and the Cl, which is the chlorine, dissolves into the glass water, and yeah, basically as time moves forward, they'll be in equal concentrations everywhere. So when the cell is placed in a solution of potassium chlorine, potassium will rush into the cell through the open potassium pores, leaving the negatively charged chlorine behind. The net charge will then change from neutral. The initial net charge um, of the the potassium chloride, I believe that's potassium chloride solution, was zero because every potassium by the was balanced by a chlorine. So as potassium ions move into the cell, a large electric force builds rapidly outside the cell membrane. This force acts in just the opposite direction to the diffusion force. It pulls potassium outside the cell. In the end, the potassium is distributed inside and outside the membrane so that the opposing diffusion force and the electric force are equal. There is, of course, constant shuttling of some potassium back and forth, but the net movement is zero. So basically, the system has reached dynamic equilibrium. Yeah, that makes sense because dynamic equilibrium is when um is basically when the forward reactions and the reverse reactions are like the rate of the reactions are equal. So basically, at this point, the ratio between like the reactants and the products, they remain unchanged over time, which makes pretty much sense because um, the potassium is like is being constantly shuttled back and forth. Okay. So the electric force, I think I think how I interpreted the electric force is that it is um basically it's just a force that is exerted between any two charged objects. So basically it shows that as the amount of charge on the objects increases, the force between them also increases. But as like the But however, if the distance between the charged objects they increase, the force between them actually decreases. So yeah. So these are just actually knowledge that I've already learned in my AP chemistry class, and it's a great thing that I did take that class before taking this physiology class, because it's definitely helped me understand the kind of process being told in this text. Okay, so the situation I have described for the cell also applies to artificial non-living membranes if they are semi-permeable, meaning that they let some ions, such as um, the potassium, pass through freely, but not others, such as the larger protein ions, P, P2 negative. Is that type phosphorus? I don't know. I might have to look what this is, what element or the compound this is. But it looks kind of looks like diphosphorus. Okay. So a semi-permeable membrane can function whether it is a part of a living cell or not. No biological energy is required for the ions to distribute themselves across the membrane. Indeed, the Nernst equation, which is something that I already do know, I've learned it in my AP chemistry class, was developed many years ago to describe the function of semi-permeable membranes, both living and the dead. This equation simply makes possible calculation of the potential difference across the membrane that will exist when a given type of ion has reached equilibrium, that is, has reached stable concentrations on both sides of the membrane. It is assumed that the ion in question can diffuse freely across the membrane. Okay, two things to remember from this paragraph: semi-permeable and the Nernst equation. So basically, the semi-permeable means that it is something that is usually permeable to some that is usually small molecules, but not like other usually large particles. Yeah. So the Nernst equation. So basically, in terms of context of physiology, the Nernst equation I think is used um, for finding the electric potential of a cell membrane with respect to one type of ions. Basically, I think I could definitely link this back to the acid dissociation constant, which is what something that I learned from AP chemistry. So yeah, basically it describes how like the equilibrium potential for like an ion species is like related to the concentrations of the ion species on like the other side of the membrane, permeable to the ion. So so yeah, like for example, cell membranes, I think they're often more permeable to potassium as mentioned in like the earlier paragraphs. And so like the concentration of like the potassium inside the cell is like greater than the concentration outside of the cell. So in that way, like the negatively charged ions balance out the positive charge of the potassium ions. So like the so that the charge inside and the outside of the cell is neutral. And yeah, that means that the membrane is assumed to be like permeable to anions. Okay, so here is the Nernst equation. I think this paragraph kind of tells the meaning of the constant meaning of the equation here. But just to kind of test out my knowledge, I won't read this paragraph first, and then um I'll explain what these various letters in the equation mean, just so I can test out my knowledge from what I've learned in AP chemistry. Okay, so V, I think that's the equilibrium potential, or basically known for the Nernst potential for the given ion. So R is the universal gas constant. I think it was equal to 8.314, yeah, 8.314, um 8.3144, I think it was joules per Kelvin times mole. Oh, joules per Kelvin per mole. Okay. So T obviously that's the temperature in Kelvin. So all you have to do is just to get Kelvin, if you're given the Celsius, all you have to do is just add that number to 273.15. Okay, so Z, or also known as K in this case, I think this is the valence of the ionic species. I think K in this case is the valence of the ionic species. Okay, so F is the. Oh, okay. I think F is the Faraday's constant, and I believe it was equal to 9,000. It was 9,600. 9,600. Wait, no. 96,485. Or was it 6? 485. It's around that. It's around that number. I'm just gonna check later. It's 96,465 coulombs per mole. I think that was the unit. Coulombs per mole. So the upper part right here, the I. I think that's an I. That's an I plus. I plus. I think that's the concentration of the ionic species in I. I think that's the. Yeah, I'm not sure about that one, but I think that's the concentration of the ionic species in I. But in. Is it the extracellular or intracellular? Well, it has to be the extracellular, right? Because in the equation, yeah, it defines. Okay. So that means that the one on the bottom right here is the concentration of the ionic species in I, and it's for the intracellular, I think. Okay. Yeah. I think I've learned this topic, the nurse equation, when we in AP chemistry when we were talking about thermodynamics. It was one of the last topics that we learned, but the equation kind of looked a bit different, but it's basically the same. So, same. So where K, R, and F are constants, yeah, that's what I said. There, R is the universal gas constant, F is Faraday's constant, and K is the K. I think is the valence of the ionic species. I don't know. So T is the absolute temperature, and A plus and I plus is the concentration of positive ions. So under standard conditions of pressure with the temperature of 18 Celsius, the temperature appropriate for optimal functioning of the squid axon, by the way, but not for mammalian cells. And the voltage expressed in millivolts. The equation becomes okay, so they converted the equation. So V in millivolts is equals to 58 log, okay, for positively charged ions. Okay, because they. Okay, so because they changed the conditions of the pressure and the temperature. Okay, so it's different in when the voltage is expressed in millivolts, but I think it's. Is it the same from this one? Or is it just. I'm not sure about that. Okay. So let us now measure the concentration of potassium inside and outside the cell. Common values expressed in the concentration units are millimoles per liter. Millimoles per liter might be potassium Al is equal to 20 millimoles per liter, and potassium N is equals to 400 millimoles per liter. Putting these values into the nurse equation gives us. Okay, so basically substitute these values for the ones right here. Okay, so V is equals to 58 log. So you can see here 58 log, and then divided 20 and over 400, you get 0.0500, and then multiply them. Okay, where did this come from? Oh, okay, they got it. Okay, So it's equal to negative 75 millivolts when rounded off. So based entirely on the concentration of potassium inside and outside the cell, the Nernst equation predicts the membrane potential ought to be negative 75 millivolts inside relative to the zero level outside. When the actual cell membrane potential is measured with a microelectrode, it turns out, in fact, to be negative 75 millivolts inside relative to zero outside. The membrane potential of the cell is determined entirely by the concentration of potassium inside and outside of the cell. Implicit in the Nernst equation is the basic assumption that the ion in question can diffuse freely across the membrane. So we can conclude from our results that for this cell, the membrane is freely permeable to K plus or potassium. Yeah, just like what I mentioned earlier in this paragraph. Yeah, so basically the potassium ions, um, so during the typical resting membrane potential of like a cell arises from like the separation of like the potassium ions from the intracellular. Basically, they're like relatively like immobile anions across the membrane of the cell, which means that potassium is definitely permeable for this cell membrane. So the mechanism underlying the resting potential membrane in neurons is basically the same as in the idealized cell used earlier as an example. The resting potential is determined mostly by the distribution of potassium inside and outside the cell. The concentrations of common ions inside and the outside the I assume it most okay. Inside the squid giant axon are given in table 3.1. Most of the potassium inside the cell. Application of the Nernst equation to the potassium concentrations in the squid giant axon gives a resting potential of negative 75 millivolts, the same as for the ideal cell. However, when a microelectrode is inserted inside the axon to measure the actual resting membrane potential, it turns out to be perhaps negative 70 millivolts. Hence, there is a small but important discrepancy between the actual voltage and the voltage predicted by the Nernst equation, applied to the potassium concentrations in the squid giant axon. Okay, so I didn't know that squids actually do have a giant. They do have giant axons, but in case of like, you know, in this class like physiology, um, I think, yeah, I think using the squid giant axon is pretty um useful since like the cytoplasm in the axon can be like extruded and then they can be used for like studies using its composition. So yeah, so since um okay, so let us reconsider the ion channels in the nerve axon membrane. Figure 3.5. Only the open channels are involved in the resting potential. The, the gated channels remain closed. Most of the potassium channels are of the permanently open type, but there are also potassium channels with gates. Potassium cannot cross entirely freely because not all of the channels are open. Okay. Potassium cannot cross entirely freely because not all of the channels are open. Okay, let's just go look back at the figure 3.5. She's talking about this one. Yeah, as you can see, There are gates, but there are also ones that are open. So the chlorine channels on the axon membrane are of the open sort. However, there are not as many chlorine channels as potassium channels. Chlorine can cross back and forth through the membrane, but not as easily as potassium. In fact, potassium can cross about twice as easily as chlorine. Most of the chlorine is outside the cell. Typical concentrations will be 30 millimoles per liter inside and 590 millimoles per liter outside. Table 3.1. Okay. Okay. So yeah, 30 on the inside, but 590 on the outside. Application of the Nernst equation to chlorine concentration gives a value for the membrane potential of about negative 75 millivolts, which is close to the actual value of the resting potential. It should be noted that in the Nernst equation, the upper and the lower concentration terms are reversed for negative ions such as chlorine. Oh, okay, so basically the unlike the initial Nernst equation that we use right here, where um, the upper and the lower concentrations um, are right here, which the outside is at the top and the inside is at the bottom. But in case of the chlorine, the inside should be at the top and the outside should be at the bottom. So yeah, like in this portion right here. So it seems that chlorine may also play some role in determining the resting membrane potential. Okay, I just realized that I've been saying chloride wrong. I've been saying it as chlorine, but in my mind, I was thinking that I was saying it as chloride. But yeah, from now on, I'm just gonna um say it correctly. And I'm so sorry if you guys kept hearing me saying that this is chlorine, this is chloride, because there's a negative in the end. Okay, so yeah, it seems that chloride may also be played some role in determining the resting membrane potential. So the sodium channels in the axon membrane are numerous, but also all of them have gates. They are closed. Only a few very channels are always open. Sodium can cross the membrane only about 1/20th as easily as potassium. In essence, um, sodium is kept out of the axon. When the Nernst equation is applied to the concentration of sodium inside and outside the cell, table 3.1, which one? Sodium inside 60, outside 436. So, a predicted value for the resting membrane potential of 450 millivolts is obtained, marked differently from the actual level. Oh, I thought that was four. That never mind. That was positive 50 millivolts is obtained, marked differently from the actual level of about negative 70 millivolts. It seems clear that the sodium cannot play an important role in determining the resting membrane potential. So yeah, basically this paragraph is saying that one of the reasons for why sodium can be used to determine the resting membrane potential level is that because most of like the ions like cannot move freely across the cell membrane because it's like not permeable to most ions. So, like for example, if let's say that potassium is like a positively charged ion that has like the intracellular concentration of like 14, let's say like 14 millimoles, and it has like an extracellular concentration of let's say 140 um, um, millimoles, and the that will mean that the equilibrium potential value of like positive 65 um positive C 65 equilibrium potential value of like positive 65 millivolts. So I think that that difference means that when the inside of the cell is like 65 millivolts higher than the extracellular environment, then that will mean that potassium will be in like the electrochemical equilibrium across like the membrane. So yeah, like potassium, like we know the potassium is like a um yeah, like a positively charged ion and stuff like that. I was gonna give an example, but I forgot what I was gonna say. But I'll try again later. But yeah. Okay. So the Nernst equation gives the right value for the membrane potential only if an ion can diffuse freely across the membrane. Hence, the value of positive 50 millivolts obtained when potassium is put into the equation tells us that potassium cannot diffuse freely across the membrane. Because a few potassium channels are open, we might expect that potassium makes small contribution to to the membrane potential, and it does. So yeah, kind of connects back to the example that I gave earlier. Okay, so Alan Hodkin, Andrew Huxley, and their colleagues at Cambridge University in England did the classic studies that led to a much greater understanding of the nerve membrane resting in action potentials, using the squid giant axon as their model of the neuron membrane. They also developed the mathematical equations that explain how ion concentrations and ion movements across the membrane generate the resting action potentials. I think it's talking about the Huxley equations. I don't know why, but that was super hard to pronounce. But yeah, the Hodgkin Huxley equations, which I do actually did learn that for AP chemistry. Okay, so where were we? Okay, here. So they shared the Nobel Prize for this work. Early in their studies, they also observed the behavioral function of the giant axon. They stimulated it and anesthetized. Oh my god, let me pronounce this right. Anesthetized squid. Okay, anesthetized squid. Whereupon the body mantle contracted and smashed the recording electrodes. Fortunately, the axon can be removed from the animal and kept alive and fully functional in a dish containing appropriate solutions. So, yeah, that's pretty cool to know how they used the squid giant axon in their earlier studies and then connected it back to like future learnings that they find. In their studies on the resting membrane potential, Hodgkin and Huxley varied the concentrations of different ions inside and outside the squid giant axon. This axon is very hardy. The interior substance, the exoplasm, can be squeezed out like toothpaste from a tube and replaced with various solutions of ions without killing the membrane or disturbing its functions. Hudkin, Hudkin and Huxley found that the resting potential of the squid giant axon membrane was determined very closely by the concentration of potassium inside and out. This relation holds only for potassium. Manipulation of chloride or sodium, and it has much less effect on the membrane potential. The relation between potassium concentration and membrane potential is not quite perfect because, in fact, chloride and sodium are making small contributions. So yeah, Hudkin and Huxley used like the used like the large ions of the squid to kind of measure like the voltage changes during the action potential. Just to kind of summarize what the paragraph was saying, I think basically they found that like the membrane potential of like the neuron is actually reversed during like the action potential, which causes like the neuron to like momentarily have this positive membrane potential. And this kind of like rapid reversal of like the membrane potential was kind of like, it was, I would say, yeah, it was a pretty significant discovery, especially um it's when it's used for like understanding like the process of like the underlying process of like the action potential. Okay, so the Nernst equation can be expanded to incorporate not just one but several ion concentrations. This expansion, called the Goldman equation, which is actually something that I'm not familiar with. I don't think we ever talked about it in my in my AP chemistry or in the AP biology class. So yeah, this expansion is also quite simple. The only new term in the Goldman equation is the permeability P. This is a measure of the degree to which a given ion can diffuse across the membrane. As we noted above, the axon membrane is the most permeable to potassium, only half as permeable to chloride, and 1/20th as permeable to sodium. Using these permeability values, Hodgkin and Huxley applied the Goldman equation to the squid axon and found that it predicts the resting membrane potential exactly. Remember that the Nernst equation assumes that the membrane is freely permeable to the ion in question. For example, potassium. In fact, no real membrane is completely permeable to any ion. The Goldman equation takes this into account and uses the actual permeability of the membrane, which is P, for each type of ion. So yeah, basically I think the Goldman equation is um used to kind of like determine like this reversal potential across like the cell membrane. And yeah, as mentioned, it takes into the account all of like the ions that are permeant through the membrane. So yeah, possibly like I'm not sure yet, but since it takes into account the like the actual permeability of the membrane for each type of ions, then it might mean that like the Goldman equation takes like other ionic conductances into the account, and it may be used to calculate the membrane potential using like relative permeability, and like possibly maybe like the concentration of all the three ions. So yeah, the nerve membrane potential will remain constant at about negative 70 millivolts, if only if the ion concentrations, particularly of that of potassium, remains relatively constant. There is certain to be some leakage. Um, so sodium is under strong diffusion pressure to leak in, since it is present in a much higher concentration outside the cell, and some sodium will leak in. Leaking of sodium through the membrane will increase the positive charge inside and encourage some potassium to move out along its diffusion gradient from the high concentration to the low one inside. Okay, so Na sodium under strong diffusion pressure to leak in, much higher concentration outside the cell. Okay, got it. Okay. The system ought to run down eventually. It does not, because a mechanism, oh my god, a mechanism in the axon membrane actively pumps sodium out of the cell and potassium into the cell across the membrane. The pump requires a significant amount of biological energy in the form of adenosine triphosphate (ATP) to work, It must move the ions against their concentration gradients. The pump does not move the ions fast, but it is always steadily at work. It pumps just enough to maintain the potassium and the sodium concentration at constant values inside and outside the cell. Okay, so ATP is this kind of like protein pump that is found in the cell membrane. And so, yeah, based on the meaning here, it's basically used to transport sodium and potassium ions across the cell membrane. And yeah, um, so the way the sodium potassium pump affect like the membrane potential is that it kind of helps to maintain this equilibrium in the membrane potential in the cells, since like the sodium and the potassium move against the concentration gradients as mentioned in the text. Hodgkin and Huxley showed the importance of the pump with some simple experiments. They poisoned a squid axon with cyanide, a deadly poison that acts to block the formation of ATP, the source of biological energy that powers the machinery of the cell. At first, nothing happened. The resting potential remained constant and action potentials were conducted normally. The action potential will be considered later. Gradually, however, the axon began to run down and finally ceased to conduct action potentials. Hodgkin and Huxley then added ATP to the axon and found that it returned to its normal level of functioning until the ATP was used up. We can draw two important conclusions from the cyanide effect. First, maintenance of the resting potential and the conduction of action potentials do not require the immediate use of biological energy. However, the pump does require a constant supply of energy, and in the end, it is the pump that maintains the ion concentration at their constant levels. Figure 3.7. Okay, so we can see active pumps. The ion concentrations in turn produce the resting membrane potential, and as we shall see, are the source of energy that drives the action potential. The action potential indirectly runs on biological energy supplied by the pump. To some, okay. So, to summarize, the nerve axon resting membrane potential of about negative 70 millivolts is due largely to the concentration of potassium inside and outside the cell. Much more potassium is inside than outside, and involves a passive process of ions moving through permanently open ion channels, as you can see here in figure 3. The open channels and the pumping of the ions. So the distribution of potassium is due in turn to the presence of negatively charged proteins inside cells. Hence, the concentrations of ions are of the result of the opposite action of the diffusion force and the electric force. The diffusion of chloride and sodium is much less important than that of potassium, but these ions do contribute a bit to determine the resting membrane potential level. The ion distributions are maintained at a steady state by a pump that uses biological energy (ATP) um, to pump sodium out of the shell and potassium in. So yeah, I think figure 3.7 kind of visualized this. As we can see here, potassium ions are being um, pumped in, and the sodium ions are being pumped out. So action potential. The most important fact about the action potential is that it travels down the axon. So actually, I do know what the action potential is. I've learned it quite a bit in my AP psychology class, and I think it kind of helped me prepare for all of these neuroscience talk for this topic. So in a typical neuron, it begins at the point where the axon leaves the call body and travels down to the axon terminals, which synapse on other neurons on muscle or gland cells. Figure 3.8. The large and rapid change in voltage across the axon membrane, that is the action potential, develops at the beginning of the axon and at first involves only a very small, and the text ends there. So, yeah, I think I definitely understood what this whole text is talking about, and it introduced me to some new concepts that I did not initially knew about, such as the Goldman equation. And yeah, I think there's definitely some a bit of other information that I might have to look up and need some clarification, but overall it's very understandable. And yeah, um, this pretty much concludes my um, third Think Aloud assignment for the Reading Aloud assignment. And yeah, I hope you enjoyed listening to me doing thinking aloud and talking about the text as I move forward and the learn more about the cell membrane potential and the different types of ions. But yeah, so thank you so much for listening, and have a nice day.